Hi everyone. Today we're going to talk about a LSTM based method for end-of-life prediction of lithium-ion battery. Lithium-ion batteries have become the mainstream power source for electric vehicles with relatively superior performance. However, battery aging and performance degradation due to the external environment and internal factors which should be reflected in the evaluation of the state of health. Accurately predicting state of health can improve the overall life of the battery and support safe driving in electric vehicles. At present, there are many prediction methods for state of health. Here, we propose a end-of-life prediction techniques based on LSTM method.
Lithium-ion batteries are now widely used for many applications such as home appliances, smartphones, power tools, energy storage systems, and electric vehicles because of high energy density, high electromotive force, high output voltage, low self-discharge, low voltage drop, and easy management. However, battery degradation begins immediately after batteries are manufactured and will be replaced 70% or 80% of initial capacity for safe operation. Thus, it is important to predict when battery life will be over.
In a battery management system, state of health is an indicator that describes the health status during the degradation of lithium-ion batteries. In general, it can be expressed as the ratio of the current available capacity to the initial capacity, so that we can estimate a state of health as a functionality indicator or a quantified health status of batteries. The definition of remaining useful life is fairly clear and straightforward. It indicates that how many cycles remain from now to the estimated end of life. And we're going to talk about the end of life in the following page.
Before we start discussing neural networks, we can talk about an health indicator batteries, which is called end of life. What is end of life? The end of life for battery is exactly that, the moment where the battery reaches the end of its usefulness and lifespan and can no longer operate at anywhere close to the peak capacity that you once enjoyed. It's important to note, however, that end of life does not mean that your battery will suddenly become useless after a certain amount of time has passed. Far from it. It simply describes the total amount of time that you can expect your battery to operate at peak performance. The end of life for lithium-ion battery is usually 80% of its initial capacity. What happens to battery at end of life? Despite no longer operating at peak performance, the end of life battery still hold 80% of its initial capacity. These batteries have the immense potential to be repurposed into second life batteries for use in less demanding applications like stationary energy storage.
The curve of batteries degradation, as we can see in the right side figure, this curve is very complex and irregular and affected by many factors. However, the data was correlated with cycle in real time. Thus, within the LSTM, which focuses on dealing with time series data, could be a great choice to predict the curve. Before we send data into the neural network, we have some steps to do first. The training set is the data before 50th cycle, and the testing set is the data after 50th cycle. Also, we normalize the data to prevent the problem of gradient vanish and explosion. According to different demands, the input and output of the LSTM layer can commonly be divided into one-to-many, which means using one sample point to predict more than 3 data points. Many-to-one, which use few data points in the past to predict 1 point. And many-to-many equals use the past data to estimate the trend in the future. In the battery situation, we prefer to say the many-to-one structure. The model structure was LSTM and Java layer across to build, and the last layer is dense layer with 1 unit. After building this model, we fine-tuned 3 parameters: the units of LSTM, the dropout rate, and the epochs of fitting.
This page shows the prediction results of LSTM and NN without turning any parameters. The figures show the cases of unadjusted parameters. Figure 1 shows that the prediction result of NN is 23 cycles after the end of life. And Figure 2 shows that the prediction result of unadjusted LSTM is divergent. And this page shows the LSTM prediction results after parameter adjustment. It shows that the LSTM result after adjusting the parameters is quite ideal. But the prediction result in Figure 3 is 14 cycles after end of life occurs, while the prediction result in Figure 4 is 9 cycles before the occurrence of end of life. It shows that there is a large part of the predict curve is included in the 95% confidence interval, and the occurrence of end of life can be predicted in advance, which actually predicts the end of life.
In this page, we're going to try to improve our algorithm by considering the following factors in the future. In this figure, those spiky points on the blue curve are actually the product of resting period, which is called CRP, capacity regeneration phenomenon. And what is the resting period? For example, like electric vehicles standing still at a parking space without being charged or discharged. And a period of time in this situation is called resting period. The regenerated capacity during the resting period could prolong the useful life of batteries, which means that resting period is a factor during the degradation process of batteries. The CRP, or the resting period, is considered to be a randomity, since the condition that you leave your car to a standing still in a parking space is randomly happened. And that occasional scenario is related to user's habit or human behavior, which can be described as a randomity. Therefore, detect the CRP, or resting time, to label and categorize the degradation data might be a way to fit the bill in order to realize an improvement of state of health estimation or remain a useful life prediction of lithium-ion batteries on practical usage. And this is the end of the presentation. Thank you for listening, and wish you have a nice day.